Hi class, welcome to the next section in chapter 5. This is 5.4. Today we're going to talk about related rates. So this is how another method in which we use derivatives to solve word problems is probably the easiest way I can explain it. So let's just go ahead and get started. So a related rate problem is when you're given a situation where they tell you that one element changes in relationship to another element. Okay, so a common example of this is if you're blowing up a balloon, right, that the rate at which you are blowing air into the balloon will cause the volume of the balloon to expand at a certain rate, right? So there's a relationship there. The faster you blow into the balloon, the faster the volume expands, right? The slower the rate in which you are putting air into the balloon, the slower the rate at which the volume expands. So there's a relationship between that, and that's what we're going to be talking about here. So this is very word problem heavy. So our approach to these are like it is for any word problem. Read the question several times, draw a picture, try to write some relationships. Generally you'll be given a function. If not, you should know what the function is that you're using or how to find the function that you would want to use. Like for instance, if I'm talking about volume of a sphere, right? If I'm blowing up a balloon, that's pretty much a sphere. So if they don't give me the volume of a sphere, I would need to go and find the equation for the volume of the sphere and use that. Okay. There's a lot of implicit differentiation that happens in this section. So just be very cognizant when you're working through these problems that you say, okay, you know, if my independent variable is time, right? As time goes on, this is changing or this is changing. Just make sure you know what's changing, right? As time goes on, what are all the things that change? So then when you differentiate your equation with respect to time, you know that these are all different functions of time, right? So for when you do your implicit differentiation, that's probably the best advice I can give to you for this section. So let's kind of put that into paper, right, onto paper, and then let's do some examples. So again, generally we're talking about how things are changing over time. That's pretty much almost always the input variable that we have. Sometimes it's distance or position, but generally time is what we're concerned with. Okay. It's very important to identify the things that are changing, as I said before, right? So I'm talking about, again, a balloon being blown. What are the things that are changing? Well, the volume is changing. The surface area of the balloon is changing. The rate of the amount of air that's inside of the balloon is changing. So we got to really just make sure we know what are the things that are changing over time, right? What is my input variable? Again, most of the time it's time, but not always. Okay, sometimes it is distance. So what is changing? What is my input variable? And is there an equation that binds all of these things together? And if so, what is that equation? And again, understanding that I'm probably going to have to differentiate it implicitly, so there's probably more than one function there that changes over time, right? So again, we're generally going to need to differentiate implicitly with the chain rule because we're going to have two or more variables that change in relationship to our independent variable, which is, again, generally time. So I said the same thing like maybe 3 or 4 times already, so we're going to do it one more time as a problem-solving strategy list, right? Always, number 1, read the problem carefully. Okay, so I've said this numerous times. I generally read a word problem about 4 to 5 times, right? I'll read it once. I'll read it again and write down some important pieces of information. I'll try to draw a picture and read it one more time and label stuff on my picture as I read it. You're going to have to read your word problem generally a few times over. Okay, so again, I like to draw a picture as well. And I like to introduce notation, preferably into my diagram. If not, just writing on the side, a little bit of scratch work, and trying to assign symbols, especially those that change over time or that are related to time. Okay. Then I want to try to form an equation, right? And I should definitely have some derivatives in that equation. So basically 4 and 5 are the same thing, right? So here I said express given information and the required rate in terms of derivatives, but that kind of has to do with writing the equation, right? Taking an equation from 3, forming derivatives from it, and then putting those into your bigger equation for 5. Okay. So let's go ahead and do some problems. Okay. So 7 is substitute our stuff back in. Okay. So we're gonna have an equation. We got to substitute stuff back in. Really, what 7 is saying is make sure you provide the answer that the question is asking you. Okay, because it's very easy to get to an answer, but then you're not actually providing your final answer that they're asked for. So make sure that you are answering the question. Okay. So let's go ahead and do an example. So let's say that we have a 10-foot ladder that is resting against a wall. This wall is vertical, it's straight up. The ladder is going to fall, right? And the way that it falls is that the bottom of the ladder is going to slide away from the bottom of the wall. So as it slides away from the wall, the top of the ladder slides straight down along the wall to the ground. Okay. I know that the bottom of the ladder is going to slide away at a rate of 1 foot per second. Okay. I want to know that if that is what the rate of the bottom of the ladder is moving, what is the rate that the top of the ladder is moving as it slides down from the wall? Assuming that, so not only do I want to know how fast it's going, but I want to know how fast is it moving at a specific instance, and that is when it is 6 feet from the wall. So when the bottom of the ladder is 6 feet away, how fast is the top of the ladder moving? Okay, because obviously as this moves, this is actually going to increase in speed as it falls, right? So even if this is moving back at a constant rate, that doesn't mean that this is moving at a constant rate. So, or possibly it is actually, I don't know. Let's see as we do the math, okay? But we read this together, and then I provided a picture, right? So we've done steps 1 and 2. I read the problem, I try to understand as best as I can, and I provided a picture. I haven't labeled anything. So that's what I would want to do for number 3 is start to draw some stuff, okay? So I read this again. So again, I have a 10-foot ladder, okay? So this ladder is 10 feet. So there you go, right? I'm reading it a third time, and I'm introducing notation into my picture as I read, right? I know that the bottom of this ladder is going to slide away, and it's going to move away at a rate of 1 foot per second, okay? I'm interested in when I am 6 feet. This is the exact moment in time that I'm interested in, right? So how fast is this moving downwards when I'm at exactly this distance? Okay. Again, the rate that I'm moving here is a constant rate of 1 foot per second. This is what I don't know at this moment of time, right? When it's exactly at this distance, at this instant, what is its speed that the top part is moving? So I read this twice, one time just to read it and try to understand it the best I can. Then I drew a picture, I read it again, and I started to label things. Okay, we come back here. So now we want to try to express any information that we can in the term of derivatives. So really we're trying to now put some equations on paper, right? So I've introduced some notation, I've labeled some stuff. So 4 and 5 is really just going to be me trying to form some equations and find out what my derivatives are before I start to try to differentiate a function. So here I go. I know x is changing over time, and so is y. So this is x, right? The distance away from this, right, left and right movement. This is y, up and down movement. So I know the rate at which x is changing, but I don't know the rate at which y is changing, right? Both of these are a function of time, okay? The ladder moves away from the wall, and this distance increases with time. This distance decreases with time, so x and y are both functions of time, right? So I'll call those x of t and y of t. The derivative of x is 1 foot per second, positive, that's the rate of increase. I want to know what the rate of changes for y. It should be negative, right? Because this distance is a decreasing distance and moving downwards. So it should be a negative rate of change. Okay, again, notice that the rate of change is negative because I'm decreasing in height, so I should have a decreasing value. The equation can be used, the equation that we can use to relate x and y is the, of course, Pythagorean theorem. Again, this is a right triangle because this is a right angle, right? So this is 6, this is 10. I can find this height here, but again, remember, the height here at this moment is the height at this moment. It's not the rate at which this ladder or this distance is decreasing. It's just the actual height at the moment. So what I could do is, instead of saying 6 and 10, I can call it x and 10, because again, the picture I have is for a specific moment in time. It's not always at 6 feet. I'm only interested in it when it is 6 feet. So before it reaches a length of 6 feet here, it was a distance of x, right? It's a variable. It changes with time. So it would be much easier to call this x, 10, and y, and then use my Pythagorean theorem. Okay, so x squared plus y squared equals 10 squared. So now I have an equation, which is nice because then I can do what? I can differentiate when I have an equation, and I can then substitute in my derivatives. Okay, so I replace x and y with what they are, functions, right? My x function squared and my y function squared. If I differentiate them with respect to time, okay, this does not turn into 2x, and this does not turn into 2y, okay? I know that you know that the y doesn't because it's implicit differentiation, but remember what our variable is. Our variable is time, okay? Our variable is time. Our variable is not x. X is not the variable we're interested in, right? It's time, or in this case, I'm not calling t time, I'm calling t a distance, right? It's a distance away from the wall. So when I differentiate this, I'm using the implicit differentiation method for both of these because they both rely on the same variable, right? So here, I get 2x prime, and I get 2y prime. This goes to 0. Okay. For x, I know x at this specific moment in time is 6. So I can make that substitution. Okay, if I use the Pythagorean theorem again, I'll have an actual exact value of y, right? So if I put 36 plus y squared is 10 squared, I will have that height of y for that specific instant in time. Okay, so I can plug in my x, which gives me my specific value of y, which is 8. And then I can substitute all the things I know, which is x, y, and x prime, which will leave me with the only thing I don't know, which is y prime. So I plug in my 2, my x into my derivative, right? My x prime, which is 1 foot per second, and my 2, my 8, and my y prime. So now I can isolate my y prime. So this is 12 plus 16y. When I isolate y squared, or I'm sorry, y prime, notice what happens. I move this to the other side, it becomes negative. When I divide by 16, I have a derivative that's equal to a negative value, which makes sense from my picture, right? My height here is decreasing. So, 3 seconds, right? It's decreasing. So since it's decreasing, it makes sense that it's negative, right? The top of the ladder is sliding down the wall at a rate of 3/4 foot per second, or 9 inches per second, when the bottom of the ladder is 6 feet from the wall. So it is decreasing in value, but the speed, okay, remember speed is always positive. Velocity has a direction. Here it's going downwards, but the speed of it is just the numerical value, the absolute value of that. So it's moving at a speed of 3/4 and it's moving downwards. So it's decreasing in value, but this is the rate at which it is moving. So let's do another example. I suggest this is probably one of the easier examples, so I suggest you kind of go back and do this over again just from the example. Okay, start from your example, fresh piece of paper, draw your own picture, start all over again, and see if you can get the same answer that we just got together. Okay. All right, let's move to the next example. Here we go. Okay, so let's say that we have a water tank that has the shape of an inverted circular cone. So before I even move further than that, let's just think about what an inverted circular cone is. So generally when they say a cone, they mean that you have a base and it comes to a tip, kind of like a pyramid, but circular, right? A cone. An inverted cone is just when you flip that upside down, like you would put ice cream in, okay? So it's the base is up top and then it comes down to its skinny point. So circular cone means the base is a circle. Inverted means that the base is actually on top instead of on the bottom. So it's not sitting on its base. The base is face up. And the point, the sharp tip, is pointing downwards. Okay. So here it's telling us that the base has a radius of 2 meters and the cone has a height of 4 meters. Okay. Water is being pumped into the tank at a rate of 2 meters cubed per minute. You want to find the rate at which the water level is rising exactly when the water is 3 meters deep. Okay, so that makes some sense to me. I would need to read that one more time just to make sure that I understand everything right. So we have a water tank. Its base is face up. It has a base of 2 meters. The radius is 2 meters. The height of the cone is 4 meters. So I can start to draw a picture, right? I know it looks like that. And as I read through, I'll label some stuff, right? I know what the radius is. It's 2 meters. I know the height. It's going to be 4 meters. Water is being pumped into the tank at a rate. So to me, that sounds like a rate of change, right? Because it specifically says at a rate. And I have a ratio here. So that's a pretty good giveaway that I have some sort of a derivative that's equal to positive 2. Okay. And I want to find the rate at which the water level is rising. So I would want to find the rate at which the height is increasing. So that sounds to me like h prime. And it tells me a given height of 3 meters. So I can start to label that. So I haven't labeled anything with derivatives, but I have talked about what I have so far just in terms of what it looks like, right? So total is 4 meters. This is the specific instant I'm looking for, okay? So I'm not going to use 3 yet until I get an equation and I can do a whole bunch of stuff. So this is kind of like the last step in the formula making process. But from what I have here, okay, and then understanding that I have a rate of time, and this h equals 3, and I'm looking for the change in the height, so h prime somewhere. That's important for me. Maybe I write those other 3 things on the side, right? That the volume is increasing, so this is volume, right? The derivative of volume. So v prime would be 2. H prime is what I'm looking for, and when h equals 3. So I have 3 other pieces of information that aren't necessarily useful at the moment while I'm labeling things here. So for instance, this 3 is not super helpful yet, but I would write that stuff on the side. Okay, so if I want to find the volume of a cone, as you just saw, that's what I have here. Maybe I don't know that from the top of my head. I definitely don't, right? But you should be able to figure it out either mathematically through your understanding of geometry, or you're going to have to look it up and find it. Okay, so one of those 2 things, the volume of a cone is basically the base times the height, right? Pi r squared times the height, and then you got to divide that into thirds if you want to do the height here. So that's the volume of a cone. That's going to be useful, especially since I'm given that v prime, right? The rate that the volume is increasing is 2. Well, I can differentiate this right now, or maybe I need to do it later. I don't know. But let's think about it. If I were to differentiate it right now, what is changing over time? So take a second and think about that. Okay, I'm going to give you a short pause so you can reflect and say, what changes over time? I know volume does, obviously, because that's a derivative I have. But what else is changing? Okay, hopefully you pause it for a second to think about it. If not, that's fine. So, yeah, the volume is changing because I'm putting water in it. But the height is also changing, and so is the radius of the water. So if I'm thinking about the water itself, how much water is in there is increasing. Okay, the volume of water is increasing, the height in which the water is increasing, and the radius is increasing as well as the water fills up. So if I'm talking about volume of the water, so this is volume of a cone. If I'm talking about the volume of the water, which I am, right? What's happening to the water as it's being filled and it's at this point in time, my derivative, my function v here, has two other things that change over time. The volume does, the height of the water does, and the radius in which the water sits inside the cone does. Okay, so as water is pumped into the volume, as water is pumped in, the volume increases, the height of the water increases, and the radius of the water also increases. So again, that's us going back here and saying, all the way over here, okay, introduce notation, assign symbols, we already did that, express the given information and the required rate in terms of derivatives, right? So what is it that's changing over time, right? Write an equation that relates to various quantities. So we're not really here yet. We're still kind of on 3, right? We introduce notation, we have some symbols, and we want to identify all the things that are functions of time. Okay. So coming back to where we were. All right, so we've identified the things that are changing with time. We need to find the height, volume, and radius when the water is 3 feet deep, because that's part of our equation. Okay, so so when it's 3 feet deep, I don't know what the height is, okay, and I don't know what the radius is. So when it's 3 feet deep, I need to find volume, radius, and height, because I'm really interested in what's happening here, not here in total, but when the water is this deep. Okay, so if we take the derivative here, we are going to get that v prime is, so this is going to be the product rule. So depending on how I want to think about it, the 1/3 can go with h, or 1/3 and pi can go with h, or 1/3 can go with h and pi can go with r squared. It doesn't really matter. But it'll be the product rule, right? It's one function times another function. So differentiate the h, keep the r the same, add to that h being left alone, and differentiating r. Since r is squared, I take the product rule. They are both functions of t, but t is not there explicitly anywhere. So everywhere I see a function that's changing over time, I use the product rule, okay, or chain rule. So I want to simplify this because I'm obviously going to be using this quite a bit. It's very clear to see that I have a common factors of 1/3, of pi, and at least one r, right? This has 2 r's, this has 1. So I can at least pull out 1 r if I wish. So I can simplify it to look like this, which is a little bit easier to work with. I have my constants on the outside, and then with one function, and then what's going on here. So it would be wonderful if I just plugged in 3 right now, and then the derivative that I have. I know that the derivative of volume is 2. I know that the height that I'm interested in is 3. I don't have a change in height, which is what I'm looking for. The h prime is what I want at the end of everything. However, I don't know the rate at which my radius is changing, and I don't know what the radius is when I'm at 3 feet. I don't need to know the volume necessarily when I'm at 3 feet. Okay, possibly I do to help me find this radius, but let's see what's going on here. In order to do this, what I really need to do is I need to use similar triangles. So what I'm going to do is I'm going to take this cone, and I'm just going to take a slice. I'm going to take a slice right down the middle through the biggest part, right? And so what that's going to do is it's going to give me a triangle. And I'm going to take that triangle, and I'm going to have my regular full-size triangle, okay, without the water, and then I will have some generic value of h, and I'll use similar triangles to form a relationship. Okay, so my regular triangle is 2 meter radius and 4 meters high. I'm interested in some generic height. Okay, in this case it's 3, but for right now let's just keep it h. And when it is h, it is a radius of r. Okay, so these are similar triangles, so that means any ratio I have for the larger triangle, the smaller triangle has the same ratio. So I can use those ratios to form an equation using similarities. Okay, so h over r is 4 over 2, right? So the height over the radius is the same of the small triangle is the same as the height over the radius of the large triangle. So I have h over r is 4 over 2. Solving that for little r, I get 1/2 h, which is nice because I actually know what h is, right? Okay, but it's nice to keep it generalized because you don't know what might happen later. But I do have a specific h, which means I know the radius when I am at exactly 3 feet high. I'm sorry, 3 meters high. So my equation for volume, which is 1/3 h pi r squared, can be replaced now everywhere. Instead of using r, I can use this formula, right? And this is always true, okay? So the volume for when I'm at 3 or at some specific height will look like this, which reduces down to 1/12 h cubed pi. Okay, so the derivative here, v prime, is going to be 3 over 12, or 1/4, h squared h prime times pi. Okay, simplify that down. So using this information now, so this is for my specific case, right? I can plug in h equals 3, because this is, again, for when I'm not exactly all the way full. For my my subtriangle, my partially filled, plug in h is 3. Okay, I know 2 is the radius of increase. Notice I don't need anything of r here. Okay, if I wanted to, though, I could plug in the r and all that stuff into the original and come out with the same thing. So we're just taking a slightly different route here. H prime, once I simplify and solve for it, is 8 over 9 pi. Okay, so the rate of increase of the height is 0.282942111 meters per minute. Okay, so that's for the height. So the height of the tank is increasing. If I cut this down and round now, 0.2829 meters per minute when the water level is 3 meters high.